Section 2.4, Connecting Differentiability and Continuity. Determining when the derivatives do and do not exist. Differentiability implies continuity. This statement is essential all over the place on the AP test. So if a function is differentiable, means it has a derivative everywhere on the graph, that implies the graph was continuous to begin with. All right? Now, continuity does not imply differentiability. The inverse statement is not true. If I say it's continuous, I can't imply it has a derivative everywhere. And I can describe that in some pictures we're going to talk about down here. Now, this statement right here, if f is differentiable at x equals c, then f is continuous at x equals c, which is a statement that relates back to this, which is important as well. So these ideas are very important to remember at times with very picky AP type questions. Now, sketch 4 unique graphs where the derivative does not exist at a given point. So, several different graphs you could have. One of them is a graph that maybe goes like this, and then it goes like this. Now, because at this point right here, what this is, it is a very sharp edge. And what happens is the slope coming from this side is going up, but the slope coming from this side is going down. Which slope is it? It's multiple slopes. We can't decide. So anytime there's a sharp point, sharp edge, you cannot have a slope at this point. And here's an example of continuity, but it is not differentiable. So this is an example of why this is true right here. All right. If it is differentiable, it implies it's continuous. It's always true, but this one is not. And here's an example of that. The next example I want to show is this one. And what happens is if a graph goes like this, and then it goes vertical for 1 second, and then keeps going like this, like a cube root graph, this little point right here, where it went vertical, straight up and down, is non-differentiable, because there is no slope when a graph goes perfectly vertical. All right, so that is another example of continuous, but is not differentiable. So these are two examples of this statement. So you can't go vertical, and you can't go sharp edges. Now the other two are a little bit more what we've talked about with limit issues. For instance, you can't have a graph that goes like this, and then it picks up, and it goes like that. Okay, that doesn't work, because that's not even continuous. So first of all, it's not continuous, it's not differentiable. You know that because it's not continuous. Second of all, you know that it's not differentiable because there's two slopes at this particular point. All right, the last one we're going to talk about is asymptotes. So hopefully that makes sense. If you have an asymptote kind of like that, and then you have it like that, what is the slope at this asymptote? We might say it's vertical almost, but remember, vertical don't work. So asymptotes, vertical asymptotes, I should say, have no slope, so they're not differentiable, but they're also not continuous. So these two are non-continuous, which implies they're not differentiable in the first place there. So, anywho, but we have these four examples of very common spots where the derivative does not exist at a point. Now, there is no point at this one, so you can't say it's at a point, but we could say at that spot. There is no dot to the graph, but at that spot place, it is not differentiable.